Good afternoon, everyone, and welcome to this webinar about cheaper, faster, and more successful 3D printing with SmartSlice for Cura. My name is Stijn Brilman, additive manufacturing consultant at Cards 3D Printing Solutions, and this week we have a guest speaker from our partner, Teton Simulation from the US. Hello, Rick. Good morning.
Hello, everyone. It's a pleasure to have been invited to co-host this webinar with you, Stijn. My name is Rick Dalgarno, and I am the Director of Alliances and Operations here at Teton Simulation. I am our Senior Application Engineer, and I also manage our Materials Alliance and Materials Testing. In a moment, I will introduce you to SmartSlice and do a live demonstration. Back to you, Stijn.
Thanks, Rick. So today I will first explain shortly what we do at Cards 3D Printing Solutions, and then I will give the word to Rick so he can show the value of SmartSlice for Cura and how this will make your 3D printing experience cheaper, faster, and more successful. So let's start with a quick introduction. Cards 3D Printing Solutions is the preferred partner of Ultimaker and Formlabs in the Benelux region, Belgium, Netherlands, and Luxembourg. And we help our customers by enabling them to successfully implement 3D printing technology into their processes. We focus on companies, universities, and research institutes, but also consumers know how to find our webshop. With a large stock and short lead times, we ensure you get your printers, materials, spare parts, and software right on time. But we don't just ship boxes. We are a partner that helps its customers to get the most out of their 3D printing equipment. We do that with our services, because buying a 3D printer is one, but knowing how to use it efficiently is another. That's why we help our customer with on-site installations, on-site training of the operator and engineers, a help desk with short response times, and a maintenance department to keep your printer in top shape. In the end, it's not about the printer itself. The printer is just a tool. It's about the parts that you print and how they improve your processes and products. So let's take a look at some 3D printed applications. I always divide 3D printed applications in three different categories, which are basically three phases in the product lifecycle: prototyping, tooling, and end-use parts. With 3D printed prototypes, I mean all the parts you print to check if your design is visually or functionally meeting the requirements, basically to verify if the design is successful. With 3D printed tooling, I mean all the parts that are used to help you produce other parts. So these parts can be anything from manufacturing or assembly tools, but also parts to improve the safety in your factory or to control the quality of your finished products. And last but not least, 3D printed end-use parts. So printing end-use parts is getting more and more popular for lot size 1 and small series, but also for replacement parts or parts that are too complex to make with conventional technologies. It doesn't matter how you are using 3D printing in your company. It's actually not about 3D printing at all. It's about the part doing its job after printing, and it's about the value this 3D printed part brings to the processes and products in your company. So besides all these benefits that 3D printing with the Ultimaker has, there are also some challenges. As you all know, the Ultimaker hardware and Cura software is very user-friendly. You can easily import your design in Cura, choose the right print core and material, select the print profile, and hit the print button. But now the big question is, are the parameters in this profile suitable for my part? Am I sure that my part will actually be strong enough for my application? And am I not using more material and print time than my part actually needs? So with more than 500 parameters in Cura that you can tweak, it requires a lot of knowledge and experience, or a lot of trial and error, to efficiently produce the parts that meet your requirements. This means unnecessary long print times, or multiple print jobs, which means a longer lead time. But it also increases material consumption, and both print time and material will cost you money, and that means a lower return of investment on your printer, and in the end it keeps the cost per part unnecessarily high. Luckily, there's also a solution available for these challenges, and we are very excited to have our partners from Teton Simulation here today to explain you more about the SmartSlice plugin for Cura and how it makes your 3D printing experience cheaper, faster, and more successful. Back to you, Rick.
Thanks, Stein. So before we get to SmartSlice, I'll take a minute to introduce you to our company, Teton Simulation. Teton is a software company that focuses on virtual testing of 3D printed parts and optimizing additive manufacturing processes to minimize print time and material use. We were founded in 2016, and our headquarters are in the state of Wyoming, with a variety of remote offices in the United States. In short, Teton develops simulation software that enables users to print better parts faster. And our flagship product is called SmartSlice, and it is a plugin for commercial slicing programs that validates and optimizes print parameters to ensure the structural requirements of the part are met, again, while minimizing print time and material. So what is SmartSlice? Well, SmartSlice is a plugin for slicing programs like Cura and Cura Enterprise. We are also working on integrations into different slicers, and those will be announced in the future. So this plugin for Ultimaker Cura lives inside the slicer itself, and it allows you to evaluate the structural performance of an FFF polymer part. And it does this using a database of experimentally tested materials, which I'll talk about more later. And it does that in conjunction with a high-fidelity FEA model, and FEA is just finite element analysis. And those FEA models are tailored for the FFF process. So in addition to just validating the performance of your part, it can also optimize those print settings to minimize print time and material usage while making sure that the structural performance requirements are met. And by structural performance requirements, I'm just saying that the part stiffness and the part strength, those are two requirements that we refer to as your structural kind of performance requirements. So SmartSlice can optimize the print settings to meet those requirements that you define. So it's used in a lot of cases to reduce the time and the number of iterations it takes to basically design a functional FFF part. So instead of printing your part, testing it, and then doing a design iteration, and then printing it and testing it and doing another design iteration, you can do all of those iterations virtually with SmartSlice. And SmartSlice also allows you to explore a wide variety of different filaments. As I've mentioned, we have an experimental database of material data that we have collected. And so SmartSlice allows you to compare the performance of a part that's printed with, say, PLA to the performance of a part printed with maybe PETG or even a fiber-filled nylon. Now let's talk about who would be a good candidate for using SmartSlice. If you happen to be 3D printing functional parts that must meet some performance requirements, then SmartSlice could be for you. If reducing print time and material usage are important, which goes hand in hand with the third bullet point there, environmental concerns. Pretty much every company today is concerned about how much material they use. They want to avoid waste and use the least amount of materials possible, in which case SmartSlice can help because of the optimization algorithms which automatically minimize the material usage. If you are already using a simulation technology like FEA to do a structural analysis on parts made from other manufacturing methods like injection molding or milling, but you aren't sure how to apply those methods to the FFF method, then SmartSlice might be for you because we've designed SmartSlice specifically for the FFF method. Finally, if you don't have a stress analyst on your team, then SmartSlice might be for you, simply because we've designed SmartSlice to be as easy to use and as accessible as we possibly can. Most traditional FEA products, there's a very steep learning curve, and you have to have months, if not years, of experience in order to gain competence using the tool. With SmartSlice, you can really be up and running and comfortable using it in 30 minutes up to an hour, and you're all set to go. All right, so the value proposition for SmartSlice really boils down to these 4 points here. We want you as a user to have optimally engineered parts. You shouldn't have a part that's over-designed, and you shouldn't have a part that's under-designed. SmartSlice can help you figure out what that optimally engineered part is in terms of material selection and print settings. Speeding product development. As I mentioned earlier, it takes a lot of time to print a part and test it, and then evaluate the performance, and then redesign the part with different material or a different print setting, print it again, test it again, etc. It's a very time-consuming and expensive process. With SmartSlice, you do all those iterations virtually, and you get to the finish line much quicker. Reducing material costs. Again, if you're printing a part that's over-designed, then you're using too much material. So with SmartSlice, you can only use as much material as is required for that part. And then finally, reducing part testing costs. Instead of printing parts and then testing them, which takes, again, a lot of time and a lot of money, we just do all those tests virtually. So all those test costs that are typically associated with part qualification are basically eliminated when you use SmartSlice. So now that we know what SmartSlice is and who it's for, it's time to do a live demonstration of the tool itself. So what we're showing on the screen now are some green parts, and those are shelf brackets that we're going to 3D print. So imagine those shelf brackets are fastened to a wall, and then the blue part there is a shelf that rests on top of the brackets. The workflow for SmartSlice starts out just like any other Cura workflow. You select your printer. Here we have the Ultimaker S5, and then the material, which we're going to use a generic PLA with a 0.4 print core. And I'll pause here for a second because the material you choose will have a direct impact on the predictions from SmartSlice. The properties of PLA are different than the properties of ABS or PETG or fiber-filled nylon, for example. So the properties you choose here, like I said, will have a direct impact on the results from SmartSlice. Next, you would typically choose a print profile. Here I just have the normal print profile. And then you could adjust things like the wall line count or the infill density for your part. And then you just jump over to the SmartSlice stage. And when you go to the SmartSlice stage, what happens is we've removed the build plate so that you have access to all sides of the part. And at this point, we're just asking the user to define what we call a use case. And a use case is just a combination of constrained surfaces and loaded surfaces. Now, constrained surfaces are also called anchor surfaces, and these are surfaces that cannot move in space. They're just fixed. And so for this example, we're going to grab this flat surface on the back, and then we'll add a new surface and select the concave surface selection tool, and we'll grab these cylinders here where the fasteners are. Now these are all surfaces that cannot move in space. We also have surface selection tools in our custom tool set for selecting surfaces that are more complicated than a flat surface or just a simple curved surface. So if you have more of an organically shaped part, you can enter our custom selection tool and select the surface for those complicated parts. So I've defined all of the anchor surfaces. Now I'll grab surfaces for the loads. So if you recall from the picture of the shelf, we're applying a shelf to this bracket on the surface up here. And we can define, if we want to, different load directions. But the default load direction is appropriate for this use case. And we'll define a load magnitude of 200 newtons. Now, a lot of our users aren't sure which load magnitude they should use. They have a good idea where the load should go, but they're not sure what the magnitude is. So we've added a couple of helpers in here on these radio buttons to give people an idea of what load magnitudes are in terms of real world examples. Like a toddler weighs approximately 125 newtons. A young child is 250 newtons, and an adult is 1,000 newtons. So if you don't know what the load magnitude is, we give you some guidance on approximate values to kind of help you choose that value. For now, we're going to use 200 newtons, and that's it. We've defined the load case and the constrained surfaces, so we're going to jump over and define the requirements. And the requirements define how stiff you want the part to be and how strong you want the part to be. For strength, we relate that to the factor of safety. And for this part, we're going to say we want a safety factor of 2.5. And what that means is if we take the safety factor of 2.5 and multiply it by our applied load of 200 newtons, that gives us a load of 500 newtons. And what we're saying is we don't want this part to yield until the load is at least 500 newtons. And the factor of safety is used to cover things like uncertainties about the material, uncertainties about the manufacturing method, and uncertainties in the applied loading and constraints. Finally, we have the stiffness requirement, which we relate to max deflection. And so this is just the upper limit on how much you want this part to move. For this example, we're going to say 0.9 millimeters, which is saying that we don't want any region on this part to move more than 9 millimeters. And that's it. Now I can click the Validate button. And what happens when you click the Validate button is SmartSlice packages up the STL file, the material, and the print settings, and it sends all that data back to our back-end service, which is hosted on the cloud on Amazon Web Services. And we use that information and the Cura slicing engine to construct a high-fidelity finite element analysis model. So what is FEA? Well, FEA is a numerical method used to solve a system of equations, and it has applications in structural analysis, heat transfer, and several other fields of study. For structural analysis, FEA simulates the structural response of a part due to applied loads and constraints. It tells you the stresses and strains in the part, the deformation of the part, the normal vibration modes, and more. And it has widespread use in a variety of industries like aerospace, automotive, machinery, to name a few. It's been around for many decades. There's a lot of commercial FEA products out there like Nastran and Abacus, ANSYS, and a few others. We actually developed our own FEA solver, which we host on AWS. However, building an FEA model is very time-consuming, particularly when it comes to defining material orientations for anisotropic materials, for partitioning the geometry into different regions, and even meshing the geometry. So SmartSlice automates all of these traditional pain points, and what would typically take you to do hours or even days by hand takes just seconds to minutes with SmartSlice because of this automation. So in short, we have adapted FEA specifically for the FFF manufacturing method. And after the solution completes, SmartSlice is going to return the computed minimum factor of safety and the maximum part deflection. And then based on these requirements, it's going to tell you if the part is over-designed or under-designed. Something else you'll notice is that SmartSlice is blazing fast. That solution came back anywhere between 60 and 90 seconds of time. So in about a minute and a half, you get an answer to how stiff is your part and how strong is your part when printed with a specific material and with specific print settings. And so SmartSlice comes back and it gives you a computed factor of safety. And this is the minimum value here. This 1.7 means that over the entire part, there's a region in the part where the safety factor is 1.7. And that's less than our target of 2.5. If I click on this button down here, I can actually visualize where in the part those regions are. So these red regions up here, and then these red regions down here, have a safety factor that is somewhere between 1.7 and 2.5. I also see that our maximum displacement that was computed is 0.98 millimeters, and that's slightly above our target value of 0.9 millimeters. I can also plot that information in the Show Displaced Part plot. If I click that, I see two pieces of information. The first piece of information is the deformed shape of the part. That's this transparent shape here. And this just gives you a sense for how the part is deforming based on the loading conditions that you've specified. I'm also showing in this plot a blue region here. And these blue regions correspond to regions in the part where there's relatively high strain. So relatively high principal strain specifically. And strain is just another word for stretch. So these are regions in the part that are seeing relatively high amounts of stretch compared to other regions. So you can use these two pieces of information to identify regions of the part that you might want to reinforce, or regions of the part where you might want to change the shape slightly to decrease stress concentrations, for example. Now at this point, what you can do is you can make a simple change like exploring how different materials perform. So instead of PLA, I could try a generic ABS, CPE, or I could go for a manufacturer-specific filament like BASF, PAHT, CF15. And then you can run another validate and quickly see how that new solution compares to the previous solution. You can also do things like changing print settings. You can manually change the wall line count, the number of top layers, the number of bottom layers, the infill density. You can even change the infill pattern and see how each one of those changes affects the performance of the part. Now what's really powerful with SmartSlice is you can just click the Optimize button, and when you click the Optimize button, SmartSlice will automatically adjust these print settings for you. It will automatically adjust the wall line count, the top and bottom layers, and the infill percentage. And because it's going to explore that full design space, it requires more than one solution. So usually it's going to run from anywhere from about 20 to 50 different simulations. And so for that to complete, it takes about 30 minutes for this part right here. After the optimization completes, SmartSlice returns a list of 10 different solutions. Each of these 10 different solutions uses a different combination of print settings, and some even use what are called modifier meshes. You see some of these in the results shown here. I'll talk more about those in a moment. Each solution meets or exceeds the factor of safety requirement, and it also meets or exceeds the maximum displacement requirement. The top ranked solution here has the minimum print time, which is 5 hours and 17 minutes, and it uses 39 grams of material. If I hover over that solution, I can see specifically what print settings were used for that solution. So we see here at the extruder level, there's 2 walls, 6 top and bottom layers, and 20% infill. Locally, inside those modifier meshes, there's 3 walls, 7 top and bottom layers, and 35% infill density. Let's slice this part and take a look at what those modifier meshes actually represent. If I slice this part, you can see that the modifier mesh outlines are visible, but they don't affect the actual outside geometry of the part. The outer surface of the part is unchanged. But if I take a peek inside the part, you can see the effect of those modifier meshes. So where those modifier meshes intersect the part STL, we get things like extra walls and different infill densities. I can select the modifier mesh and come over here to this menu and actually see what print settings were used inside those modifier meshes. And these settings here do not have to be the same as the global print settings. For example, the global infill density is 20%, whereas the local infill density is 35%. The main advantage of modifier meshes is that it allows us to place material where SmartSlice thinks it needs to be placed in order to meet the strength and stiffness requirements. And by only adding material where it's needed, we're able to keep the print time down, and we're also able to keep the material usage down to a minimum. We'll take a look at the second ranked solution here. And you'll notice that this solution does not use any modifier meshes. So some solutions do use modifier meshes and some solutions do not. This solution here takes 5 hours and 49 minutes, so that's an increase of about 30 minutes of print time, and it uses 14 more grams of material compared to the top ranked solution. It's a little bit stronger and it's a little bit stiffer. This one uses 5 walls, 6 top and bottom layers, and 60% infill. And if I slice this part, we can take a look at what it looks like on the inside. So this part here, when you slice it, it looks just like you would expect any sliced part to be. There are no modifier meshes, so the internal structure is consistent. And there's additional solutions here that you can take a look at. Maybe you want to sort by factor of safety, and you only want to select a solution that has a safety factor of 3 or greater. So you can sort by factor of safety, and you can select one of these two solutions here, and those might meet your requirements. We want to give the user more than one solution and let the user make the ultimate decision on which solution feels the best to them and which solution meets their requirements the best. Okay, so now that we've seen how SmartSlice is used, let's take a look at some of the value you can get from SmartSlice. So a lot of our customers, what they're doing today is they're just printing solid parts because they know that a solid part is the stiffest part and it's also the strongest part. For this example, if you print that solid, it's going to take 9 hours and 44 minutes and it uses 65 grams of material. When you optimize it with SmartSlice, you can reduce the print time by 4.5 hours and you can shave off 26 grams of material. So for every part that you print there, your print time is reduced by 45% and your part mass is reduced by 40%. Now for one part, those are nice time savings, but if you imagine printing 20 of these parts, you're going to save a total of 89 hours of print time and 520 grams of material. A second approach that a lot of people do is what we talked about already. This is the print, test, and iterate cycle. That's where you print the part, you test it to see how it performs, and then based on those test results, you make some enhancements to the design. You would change the shape, or you change the material, or more likely you just change the print settings. And then you print it again, test it, and you iterate. Using some example numbers here, let's say each one of those cycles takes about 10 hours. So without SmartSlice, you can imagine that you're going to use maybe, let's say 5 of those cycles, so that would be 50 hours. With SmartSlice, you only have to do that once. You run SmartSlice to get your optimized part, and then you do your final validation where you print that optimized part and you test it just to confirm that you're getting the appropriate values from SmartSlice. So what else can you do with SmartSlice? Well, you can kind of consider what happens to the part stiffness and the part strength when you do things like use a different material, when you change the wall line count, or the top and bottom layer count, or the infill density, or the infill pattern. SmartSlice also takes into account the build anisotropy and the material anisotropy. So if you print this part at a different orientation, SmartSlice is going to tell you how that orientation affects the part stiffness and the part strength. Maybe you've got different load cases for your part, so you can look at different load cases. Same thing with those constrained surfaces. For different load cases, you might have different surfaces that are constrained. Here's an example of doing a material comparison. So this is an electronics assembly fixture printed with ABS or CPE. In both cases, the loading is the same and the print settings are the same. And what you can see here is that SmartSlice computes basically the same maximum displacement for ABS and CPE. So that means that these parts essentially have the same stiffness. But if you looked at the factor of safety, the factor of safety with ABS is 1.2. With CPE, it jumps up to over 1.8. So that means that CPE is going to be a much stronger part compared to ABS. And so you can use SmartSlice to basically select the appropriate material for your application before you print the part. So speaking of our materials database, what we've done here is that, if you think about doing classic FEA analysis or any sort of structural analysis, one of the major pain points there is figuring out what material properties to use. At best, you get lucky and find the properties with an internet search, but more commonly what you have to do is pay a test lab to generate that data, or even generate the data yourself if your company happens to have that equipment. Well, we experimentally test a wide variety of filaments, and all this data is included in SmartSlice. So you don't have to worry about tracking down and entering material properties. We've already done that for you. And to test materials, we print dog bone shaped tensile specimens that are shown on the image here. And these specimens have different raster orientations. So the XY0 has rasters aligned with the loading direction, and the XY90 has rasters that are perpendicular to the load direction. And from these tests, we can basically reverse engineer the bulk stiffness of the material, the yield strength, and the bond strength between the layers. And the data from these tests, along with something that we have called micromechanics models, allow us to compute the as-printed properties of all these various regions, the infills, the walls, and the top and bottom layers. And as I mentioned earlier, all these properties are anisotropic, which means they have, the infills got different stiffnesses in different directions, and we account for that with our FEA model. After our next release, which was actually just released about a week ago, we have a total of 45 tested materials from a variety of filament suppliers here. We've got all the Ultimaker generic materials. We have some BASF materials, some materials from Jabil, Fiber 3, Levos, Polymaker, among others. So what's included in a SmartSlice subscription? You get unlimited validation, unlimited optimization, and it's cloud-based, so that means there's no local strain on your local computer. We do have a custom on-premise deployment that's available. If that's something you're interested in, just talk to your sales rep from Cards 3D. We also offer technical support, and the license includes one named user per year. We have a full online help center that's accessible to anybody. This includes an installation guide, some tutorials to help you get up and running. There's a product tour video to give you a tour of the product, much like I did today. There's theory guides, FAQs, a list of all the tested materials, and we also let you know what's new in each release of SmartSlice. Finally, people often want to know, how good are the predictions from SmartSlice? And so what we do is we do our own validation studies, and we've done a bunch of case studies with some of our material partners to compare the predictions from SmartSlice to experimental data. And again, all this data here is available online through our blog and then through case studies on our website. So I encourage you to check all those out. That's it from my end. I'll be here for the Q&A session, but for now, I'm going to hand it back over to Stein.
Thank you, Rick, for the great presentation and live demonstration. So for everyone who has been watching this webinar, please get in touch, send us your 3D design, and let's talk. If you send us your 3D file and specify the material and load cases of your part, we will validate and optimize the parameters and run it through our ROI calculator. And then we can show you the benefits of SmartSlice for Cura in a personal meeting. You can contact us through my personal email below or through our websites cards3dprinting.com. That's the webinar for now about cheaper, faster and more successful 3D printing with SmartSlice for Cura. Thank you, Rick, for co-hosting this webinar with me. We will now move to the Q&A session.